For a century, physics treated light as a continuous wave. Then, in 1905, Einstein demonstrated that light waves arrive in discrete, localized packets called photons. Einstein linked these two behaviors mathematically. A photon's momentum, p, is equal to Planck's constant, h, divided by its wavelength, lambda. In 1924, the French physicist Louis de Broglie proposed a mathematical symmetry. If light waves behave as discrete particles, he asked whether particles of matter could behave as waves. He inverted Einstein's equation to create a new axiom for matter. A particle carrying momentum p possesses an associated wavelength equal to Planck's constant divided by that momentum. This equation carried an explicit physical claim. Matter is inherently wave-like, a property that contradicts the classical billiard ball model of the universe. In the laboratory, we control a charged particle's energy by accelerating it through a voltage, rather than measuring its momentum directly. Since the mass and charge of an electron are fixed, de Broglie's formula yields a specific rule of thumb. An electron's wavelength is approximately 1.226 divided by the square root of the accelerating voltage, measured in nanometers. This curve shows the nonlinear relationship between voltage and wavelength. As the accelerating voltage increases, the electron's momentum grows and its wavelength shrinks. At 54 volts of acceleration, the electron's theoretical wavelength is 0.167 nanometers. Applying this same calculation to a 70-kilogram human walking at 1 meter per second reveals why we don't perceive these waves in daily life. The human wavelength is vanishingly small, approximately 10 to the 35th meters. This logarithmic scale spans the physical spectrum, placing the walking human wavelength 20 orders of magnitude below the radius of a single proton. At the macroscopic scale, matter waves are compressed into dimensions far below the resolution of any physical apparatus. This is the quantitative limit of the correspondence principle. The wave nature is present, but undetectable. In 1927, Clinton Davison and Lester Germer fired an electron beam at a nickel target at Bell Labs, observing a featureless spray of rebounding particles. After an accidental leak oxidized the nickel, they baked the metal to repair it. This annealing process fused the nickel into large single crystals, with atoms lined up in regularly spaced rows. When they resumed the experiment, the classical spray was replaced by sharp, specific scattering angles. This is diffraction, a wave phenomenon where reflections from regularly spaced obstacles reinforce each other only at specific angles. The experimenters recorded a sharp intensity peak when the detector reached an angle of 50 degrees from the incident beam. To analyze this, we use Bragg's law, 2d sine theta equals n lambda. This geometric rule determines how X-ray waves reflect off parallel crystal planes. We input the known variables, the nickel crystal plane spacing of 0.091 nanometers, and de Broglie's theoretical electron wavelength of 0.167 nanometers. The calculated theoretical angle matches the 50-degree scattering angle measured in the lab. This was an exact, parameter-free prediction. It proved that a beam of solid matter scatters identically to an optical wave. Since Davison and Germer used a beam of millions of electrons, it was unclear if the wave pattern resulted from electrons interfering with each other. In 1989, Akira Tonomura at Hitachi used an electron biprism to test the behavior of single electrons. The intensity was turned down so low that only one electron was in flight at any moment, ensuring no particle could interact with another. After 10 electrons pass through, the detector records 10 random scattered dots. At 200 electrons, the impacts begin to show faint clustering. By 70,000 electrons, the dots have accumulated into clear interference fringes of alternating bright and dark stripes. Each isolated particle carries the wave mechanics within its own individual statistics. The pattern is not a collective property of a crowd, but a fundamental feature of the single electron. We are left with a conflict between observations. An electron behaves like a discrete point particle, yet it paints a distribution that only waves can produce. In 1926, Max Born proposed that the matter wave is a wave function, a mathematical field whose evolution determines the likelihood of finding a particle in a specific location. This wave function, phi of xt, is a complex probability amplitude that spreads and interferes smoothly over time. Born's rule states that the squared modulus of this wave function determines the exact probability of where the particle will land. The peaks of the wave correspond to the bright fringes on the detector. Wave-particle duality describes a single consistent object, a wave function that governs the odds, and a discrete particle that constitutes the measurement. This precise arrangement between mathematical probability and physical reality is the foundational ontology of the quantum world.